Okay, hi, welcome to my talk. I will be talking about Eevee, an AEAD mode for IoT-to-Cloud secure computation. And this is joint work with Amit, Aisajan, Elena Andreeva, and Bart. So in the setting of IoT-to-Cloud computation, imagine that you have IoT devices like fitness trackers and smartwatches, or some sensors like you have in the smart grid, electricity meters or other sensors. And these collect data, but they cannot store all the data they collect. And they don't have the processing power to do meaningful analysis on this data. So what is usually done is they send this data to some servers in the cloud, and these servers then do the processing. There are some security and privacy implications of this outsourcing. For instance, the server provider, so the processor in the cloud, can see the data in the clear, and especially if this data is like health data that is like sensitive data, then what we are interested in is to somehow protect this data from the cloud. And this is where the secure part of the IoT-to-Cloud secure computation comes from. And in our approach, there are many approaches to do this, but in our approach, what we do is we will encrypt the data locally on the IoT device using a symmetric cipher. And then we will use MPC to do the privacy-preserving data processing in the cloud. And this outsourcing works by somehow the MPC parties also get shares of the key. This can be by the IoT device directly or also by a user who configures the IoT device. And so therefore, each MPC party now has a share of the key and also receives the ciphertext. And then in the MPC protocol itself, the MPC parties will first do a distributed decryption where the key is secret shared and the ciphertext is a public value, and then they do the actual processing. And in this paper we are looking specifically at the encryption and the decryption function, and we are looking at it from a mode perspective. So what we want to do is we want to construct a mode that fits into this scenario. Therefore, the challenge that we have is that we have encryption on an IoT device and we have decryption in MPC. On an IoT device, in general, we say there are limited resources available. So somehow the encryption function has to be lightweight. So lightweight is a very ambiguous term, but for us, this means if you want to realize this encryption in hardware, it should take a small area on the chip. And if you want to realize this encryption on a software like a microcontroller, then you should have small state and it should be reasonably fast. We also have to account for the fact that in IoT devices there's a larger attack surface in general. So this also should be reflected in the mode. On the other hand, if you want to do the decryption in MPC, you want the decryption function to be MPC friendly. So this means you want a low-depth circuit, and you want full parallelizability of the decryption function, because parallelizability gives you a lot of amortized benefits in MPC. And from a mode perspective, this means we're looking for a mode that is constructed with a low overhead over the primitive calls. Especially the overhead should be low, should be linear in MPC terms. So our design is a blockwise serial mode. Blockwise and serial encryption gives you a small compact encryption, and we have a fully parallel decryption. And to account for the larger attack surface, we are considering non-Smith use resistance in the mode, and we also have beyond birthday security. This gives two benefits. We achieve high security and we achieve relatively small, we can instantiate it with small primitives. So this means a small area on chip, for instance, for encryption. And so this together is the Eevee family. And before I talk about Eevee, I will talk a bit about fork ciphers, because Eevee is a mode for fork ciphers. So fork ciphers are an abstraction of expanding tweakable ciphers. You can see the forward direction here on the slides. So in one configuration, you can encrypt the message and get a ciphertext out. This is the one-legged version. Or you encrypt the message and you get two ciphertexts out. And the security here is modeled as if you encrypt this message with two independent tweakable block ciphers. And if you invert this, then either you can decrypt the ciphertext and get the message, or you decrypt the ciphertext, get the message, and get the other ciphertext. And so you see that the fork cipher, so our mode is specified as a mode for fork ciphers, but fork ciphers are a generic abstraction that also capture tweakable block ciphers. So this means either you have a dedicated fork cipher primitive, then you can instantiate our mode with this, or you have a tweakable block cipher and you can also instantiate our mode with this because the fork cipher captures this. If you have a dedicated primitive, you can think of the cost for the one-legged version as being roughly equivalent to one tweakable block cipher. But if you have the two-legged version, then you hope that the designers of the dedicated primitive made some effort to reduce the cost so that it is less than two tweakable block cipher calls. What I also want to highlight is that for MPC, the two legs, they can be computed in parallel. So this is also gives you a benefit already there. Okay. The Eevee family is consists of three modes, and they are a trade-off in the whole space. We have Umbreon, which is a trade-off for higher security. Then we have Jolteon, which is a trade-off giving up a bit of security for more performance. And then we have Espion, which sits in the middle. And because the talk is very short, I will only talk about Espion. So this is the encryption function of Espion that is run on the IoT device. I will walk you through some of the highlights, and I hope that you get an intuition of the mode. So unlike counter modes, we will actually pass the message through the primitive. And we get a serial mode by chaining the individual blocks by putting the ciphertexts into the tweak. And then we aggregate all the messages to one message checksum. And then in the last block, we obtain the tag and the final ciphertext at the same time using the two-legged fork cipher construction. This means intuitively in the tag, all the bits in the tag, they depend on all the bits of the message because of the message checksum, and all the bits of the ciphertext because of the ciphertext chaining. So for decryption, this happens in MPC. What you can see is that the input to all the fork cipher calls is available at the start. The tag is public input, the ciphertexts are public input, and the nonce is also public input. This means that all these instances of the fork cipher can be executed in MPC in parallel. So this you can amortize a lot there. And you can also see that the remaining operations that come after the fork cipher calls are XORs, which are linear operations, so therefore they are cheap in MPC. To check that the authenticity of the ciphertext holds, you need to check whether the computed the computed ciphertext C star prime equals the ciphertext the last ciphertext that you got. Okay, now I will show you some results. So first of all, regarding security, in the paper we have a unified security proof. So even though the three instances are structurally very different, we managed to unify them in one abstraction to have a unified security proof. In the paper, we compare our modes against AES GCM and GCM SAV, and also against state-of-the-art MPC-friendly modes, of which the fastest is counter-hashed and MAC. So this table contains a lot of numbers. I will not explain everything here, but what I want to highlight is that we achieve a higher security in the nonce respecting case, and we also achieve nonce misuse resistance, and we are parallel, unlike the other previous modes. And if we want to measure performance, then what we do is we measure the encryption time on the x-axis on a microcontroller, and we measure the decryption time as the online time in an MPC protocol as the y-axis. And then you can place a dot where the mode performs. So if we are in the 64-bit non-respecting setting, then we can compare Jolteon with AES-GCM. And I forgot to say, so we instantiate, in the first time we instantiate our fork cipher using a tweakable AES construction. So therefore this is all AES based. And if we instantiate Jolteon with that, we see that Jolteon outperforms AES-GCM in both dimensions. So it's faster in software and also faster in MPC for decryption. On the other hand, if we are now moving to the non-misuse resistant setting, then we see that Espion is slower in software on the microcontroller, but faster in MPC compared to AES-GCM SIV. Now we can also use a dedicated fork cipher primitive. For this we chose fork skinny. And in the 64-bit non-respecting setting, we again have Jolteon that is compared with the two state-of-the-art MPC-friendly modes, the cross and the star. And we see that Jolteon again outperforms both. If you now want to have more security, then we also have other instantiations that give you different trade-offs depending on the size, like the size of the primitive and also the security level. I would just want to say that the cross here still has only 64 bits of security. So this is the state of the art. The other ones have higher security or non-misuse resistance. Yeah, that's all I have time for. The paper is on ePrint, and we also have the artifacts available on GitHub. Thank you.